Tomorrow we will put a big bow on all of this, as we will get every last thing that we can understand because of our derivative, because of our second derivative, be able to interpret things because of that, be able to justify things because of that, create our function based off of the information we are learning, all of that. And it does become a lot to remember. Tomorrow at the end of it, we'll kind of put it all in one place because it's been spread out throughout our notes over the last couple weeks, and putting it all in one place, how do I efficiently and calculus-wise justify different things, all of that. So adding to our list here, we talked about how we find the critical points of a function, and remember that critical points helped us identify where things like maximums and minimums can happen. And it is very generic talking because we might be talking about where the max and mins of a function are, but we could be finding max and mins of a velocity. And remember that it's all based off of whatever function we are finding the max and min for, its derivative. So if you knew that to start with, you don't need to necessarily jot that down if you're, got that list down. When we look for critical points, we always look for two things: zeros of the derivative and where the derivative is undefined. I really like this next thing for our first derivative test. If you remember, the first derivative test talked about finding where your graph rises or falls, increases or decreases, and that if you think about it will also help you identify where maxes and mins are. If it changes from increasing to decreasing, there would be a maximum there. If it changed from decreasing to increasing, there would be a minimum there. And so we can also look at that first derivative test and use it to recognize where things are maxes and mins. So based off of our first derivative, these statements right here are really going to come into play tomorrow as we talk about really using our calculus to justify where things are increasing, decreasing, maxes and mins, all of that. But just kind of recapping what we can learn because of our first derivative test. We look at the derivative of a function. If the derivative is positive, that function would have been increasing there. If the derivative is negative, the function would have been decreasing there. And if it switches from being a positive to being a negative, that means that our function would have a maximum at that point. If it switches from decreasing to increasing, that means our function would have had a minimum at that point. All right, so let's look at using our first derivative test. And I'm going to add to this a little bit. It says to find the local extreme values. We're also going to talk about where it's increasing and decreasing. And I really want us to already start putting in the justification piece, is that we are going to justify all of our answers using calculus. This one, it says for the following function, use the first derivative test to find the local extremas and where it is increasing, decreasing. One of the other things I'll always encourage you to do is, if it is a function you know something about, this is one you should know something about, an x cubed graph. Knowing something about the function can help you identify what to be expected. I know that an x cubed graph has end behavior that looks like this, right? One end heads down forever, one end heads up forever. I don't know what happens in the middle. It might twist and turn, but I know what the ends look like. Why does that matter? Well, it tells me what type of extrema I can have, right? As I'm answering this question, what type of extrema can we have? Local. We cannot have an absolute max. We cannot have an absolute min because the ends of my graph go up and down forever. So when I look at that list and I see that it's a max, I can automatically say that it's a local max because of what I know about the function. That doesn't always work because I will hand you functions that you don't know anything about, and that's okay. But utilize that part of it to really help you kind of frame some of these as we go. So first derivative test, first of all, requires us figuring out the first derivative. So that's where I would start this problem. I would go identify my first derivative. So in this case, let's see, 3x squared minus 12. Once we've gotten to that derivative, we think through its critical points. And that is, again, always in one of two places. Where that derivative equals 0 and where that derivative is undefined. So if I can set it equal to 0 and get zeros, which we can on this one, I'm going to go ahead and take out that GCF here. You can either set this equal to 0 and solve or keep factoring. And I can see that it would be 0 when x equals -2 and when x equals +2. So I got two numbers to add to my first derivative test from the fact of where my first derivative is equal to 0. Where is my first derivative undefined? It's not. That is not a function that will ever be undefined, which just means this does not add any additional points for us to look at. The difference today, kind of analyzing things, especially to help us answer the questions that are up there, when you're doing this, I would really put it onto a sign chart or a number line. So as I get all of these values, I then transfer them in order from -infinity to infinity, which it'll always be -infinity to infinity unless one of two things. They give us an interval to look at, which then I would make the ends of my number line, or the function itself adds a domain restriction to it, which then I make the ends of my number line. Okay. Otherwise, -infinity to infinity. Put that -2 on there, put that +2 on there, and then remember how a sign chart works is I'm picking sample numbers in each area, plugging them into. Now this is representing the signs of f prime. This is my derivative, right? So I'm picking numbers and plugging them into my derivative. Sample numbers in each area. So I've got a 0 at -2. Pick something less than that, like -10. If I were to take -10 and plug it into our derivative, I get -10 squared, which is 100, times 3 minus 12 is a positive number. I don't need to know what number. I need to know if it is positive or negative. Well, that's positive. Okay. If I pick something between -2 and 2, like 0. If I plug 0 into the derivative, I'd get 0 minus 12, which is a negative number. Something bigger than 2, like 10. Plug 10 into my function over here, or into my derivative over here, and I would end up with a positive number. Not my answer, but it helps me identify what's going on. So my derivative is positive, and then negative, and then positive, and what does that tell me about my function? First of all, if you think about what this is, these are the slopes. So a positive slope for my original function would have been something going like this. A negative slope means it's going like this, and a positive slope means it's going back up that way, right? So I don't necessarily have to draw a picture of it, but sometimes the picture can help me visualize what's going on here. And so for the first question, where are the extreme values? Well, because we switched from a positive slope to a negative slope, I know that this is going to be a maximum. Right? And then we already talked about on this one that I know that it's not going to be an absolute because the ends are going to go up and down forever. So I would be able to identify that as a local max. Now, what is it of? Well, that's where I just plug it back into my function. So now I'm going to plug f -2 into the original function to see what the value is of that maximum. So if I plug -2 into that, let's see, I would get, what, -8 plus 24 minus 5, 11. Okay, so I get a local max of 11 at x equals -2. Calculus justification. It's a maximum because my derivative switched from positive to negative. Good so far? The second one we see would be, it was negative slopes turns to positive slopes, which means we have a minimum there. Again, go to my function to figure out the value of that. If I plug 2 into our function, we'd get 8 minus 24 minus 5, which was like -21. And again, I know that's going to be local for all the reasons we've already discussed. Min of -21 at x equals 2. Calculus justification. F prime switches from negative to positive. Questions on that? Okay. Second question. Where is the function increasing or decreasing? So our increasing intervals would be anywhere that our derivative is positive. Our derivative is positive here, so negative infinity up to negative 2. It is also positive here, so from 2 to infinity. Calculus justification. My derivative is positive. Where is it decreasing? That would be anywhere that I had a negative interval, which would be from negative 2 to 2. And my calculus justification, my derivative, is negative. Okay. Now, a couple things going forward, and this is, again, a little bit of a learning curve, and we will, like I said, put this all onto a big sheet tomorrow. You'll see all of your justifications, or at least some guidelines to our justifications. But the biggest thing is you have to run your justifications through what you have information about directly, and it has to be calculus-based. So an example of something that they will never accept is a graph. You can't draw a picture of this. I know what the picture would have looked like, and I could have plugged in numbers, and so I know what it would look like. I can plug in values, I can find all of that, but that is not calculus-based, and you can never say, look at the graph. Okay, that's not a justification. A picture will never be a justification. A sign chart will not be a justification. I have to interpret. I have to actually say things from that to justify my answer. So you can't just say because of the sign chart. Not enough. Okay, is that making sense? All right. We have a shortened period today, so we may come back to this one if we have time, but I want to make sure that we get to the second half of what we're talking about today, which is our second derivative test before we move on to this. Can we just talk real quick? It's the same thing we just did. Your derivative is a little uglier because we've got a product here. I also want to remind you, as you think about setting that equal to 0 or zeros of something like this, if you have in a ever wondering whether e to the x can equal 0, can e to the x ever equal 0? No, an exponential cannot. Can it be undefined? No. So just keep that in mind as you're doing that. That's why that one is on there. And we might have time to go back to that, but it's the same first derivative test. Let's talk about this next concept, because this one's new to us, and that is what's called concave up and concave down. It is talking about the curve of your graph and whether that curve is opening up into the air or down towards the ground. The way that I always like to think of it is concave up. If I were to wrap my hand around the graph and my palm is facing up, my graph would be considered concave up. So it's wherever your palm would face if you were to make your hand the shape of the graph. If my palm were facing down, it is considered concave down. So what does that look like here? Something like this would be considered concave up. And again, this is your original function. F of x is considered concave up. If I were to make my hand look like that, my palm's facing up, concave up. If my palm were facing down, the graph looks something like this. That would be called concave down. Your derivatives are decreasing on concave down. Your derivatives are increasing on concave up. The second part I have listed as two things, concavity test and second derivative test. And the reason I have that listed as two different things is because depending on where you look, it can be called two different things. I kind of like that it's both because, first of all, it tells you what it finds when you call it the concavity test. It tells you how to find it when you call it the second derivative test. You go through your second derivative to identify the concavity of your graph. Okay, so the concavity test says this: the graph of a twice differentiable function is concave up if your second derivative is positive. It's concave down if your second derivative is negative. So it looks a lot like your first derivative test. but it's based off of your second derivative, and it tells us something different about our graph. Now, our graphs are not typically a parabola. We will see it pieced between being concave up and concave down. Things like something like this is concave down in this section, would be concave down. It switches and then would be considered concave up here. Okay, and tomorrow we'll talk about those points where it switches, concavity. All right, so let's go ahead and try one here. Our concavity test or second derivative test says, determine the concavity of the given function on the given interval. This one does not give us an interval, so we are just going to look. The function itself and the problem do not give us an interval, so we will look from negative infinity to infinity on this one. And if it's asking us concavity, that's your second derivative, your acceleration function. So job number one is just to get to that second derivative. So I would take the derivative initially. And then we start over, right? I take my second derivative. And very similarly to our first derivative test, our second derivative test, at this point we pause and say, okay, well, what would the critical points of that second derivative be? And we find them the exact same way we would have found our critical points earlier. Your critical points are made up of a combination of where your second derivative equals 0 and where your second derivative is undefined. So always getting our thought process through those two things. Doesn't mean that we will have both of them, but we always want to at least take a second and think about each of those. This one can equal 0, so I would set it equal to 0 and solve. Oops, that's a plus. So negative 2/3 would be where this one would be 0. That is a linear equation. Linear equations are never undefined, so never. And then just like our first derivative test, we are now going to make a sign chart, putting our critical points and our endpoints if we had any, which we don't on this one, onto our sign chart. Testing numbers, and again, this represents the signs of my second derivative, right? So I would be putting these into my second derivative to find out the signs there that will tell me about my function itself. So in this section here, I would pick something less than negative 2/3, like negative 10. If I come over here and I plug in a negative 10, this is going to be a negative number. If I come to something bigger than negative 2/3, like 0 or 10 or 100, it doesn't matter, just anything bigger than negative 2/3, plug in 10 over here, it comes out to be a positive number. And then reading and interpreting your second derivative test is it tells us about our concavity. It is concave up any place that our second derivative is positive. And the interval that our second derivative is positive is negative 2/3 up to infinity. Reason, second derivative, I guess it's called y, is positive. It is concave down. Any place that our second derivative is negative, which would be negative infinity, up to negative 2/3, and our second derivative is less than 0 or negative in that section would be our justification. Questions on that? Okay, Let's look at one more doing that concavity test here. Always good for us to kind of remind ourselves about trig functions, their derivatives, their values, all of that. So applying our second derivative test or the concavity test to y equals 3 plus sine x on the interval from 0 to 2 pi. So again, thinking about concavity, the first thing is just to get to my second derivative. So that would be where I would start all of these problems. What's the first derivative? What's the second derivative? So derivative of 3 would be 0. Derivative of sine of x is cosine of x. Our second derivative, so we take the derivative of cosine and get negative sine of x. And again, we take that equation and think about its critical points. Where is that equal to 0? Where is that undefined? Okay, now first of all, a sine curve, is a sine curve ever undefined? No, continuous function, it's never, so we'll never get a point from our undefined, but can it equal 0? Yeah, it equals 0 frequently, right? So if I set that equal to 0, this where, again, we have to remember our unit circle. Divide by -1, we're thinking about where is sine of x equal to 0. If I actually showed my algebra, it's the inverse sine of 0, right? Where is sine of x equal to 0? 0 and pi. 0 and pi. Okay. Now 0 was already on my list of numbers I was going to put on the sine chart because it's the ends of this interval. So I would start my sine chart at 0 and go up to 2 pi. So 0 is already on there. Notice this one I don't make go from negative infinity to infinity. Add the pi in there because that was one of my critical points. And then test out my sines as I pick numbers in between 0 and pi and plugging them into my second derivative. So if I think of something between 0 and pi, like pi over 2, pi over 4, something in there that you know the sine value of, okay? What is the sine value of pi over 4? Square root of 2 over 2, right? So if I put pi over 4 in here, I get square root of 2 over 2, but then the negative out front makes it negative square root of 2 over 2, right? And then from pi to 2 pi would be something like 3 pi over 2 or 5 pi over 4, something like that. So in that one, so 3 pi over 2 sine is -1, right? -1. So it's -1, then the negative on front would make it a positive, so all of our sine values are positive there. Now, with that being said, I want you guys to look at what these represented, and hopefully it makes sense. From 0 to pi would be quadrants 1 and 2. And in quadrants 1 and 2, sine is always positive, right? Then we tack the negative on, which is why it's negative there. From pi to 2 pi would be quadrants 3 and 4. Sine is always negative in quadrants 3 and 4. Tack the negative onto that. A negative negative is why it's positive. Okay, so hopefully that makes sense or kind of ties some things together there. But then answering our question, where is this concave up, concave down? So concave up again, where our second derivative is positive, which would be from pi to 2 pi. Our second derivative is positive. It is concave down from 0 to pi. That's where our second derivative is less than 0. Okay, can you guys picture a sine curve though? Sine curve, which is actually moved up 3 on this, but if you think about just a sine curve, right? From 0 to pi, do you see how 0 to pi, it's concave down? Yeah, that's what you guys just found. And from pi to 2 pi, that it's concave up. Okay, so hopefully that's kind of making sense on all of that. Yeah. All right. Your assignment is out of the book. You're doing 1 through 11. I'm going to make a small adjustment to the directions that are in the book. It's actually 1 through 6. I just had 1 through 5 up there, but the section actually goes through 6. On 1 through 6, it asks you to use your first derivative test to find your maxes and mins. Well, guys, you've already done the work, so will you also then just identify where it is increasing and decreasing, since you're just looking at the same thing you just did for maxes and mins? Just look at that sign chart and also read where it is increasing and decreasing. And then what I also don't have up here, but I want you to do, even though the book does not prompt you to, is to then follow all of your answers with a calculus justification. F prime is less than 0. F double prime is greater than 0. Whatever is the appropriate justification. Just like you saw in our notes today, add that onto your answer for each of those. Any questions?